The first type of problem we're going to look at is equilibrium problems. And in equilibrium problems, the force net is equal to 0. So the forces are balanced. So we saw this in the video on Newton's first law, where I had the people on either side of the cart of candy pulling with equal force but in opposite direction. So initially I had it set up so that when I hit go, since the forces were equal but opposite, the system did not move, so that the system was at rest, which means that when we sum the forces on that cart of candy, they equal 0 and the object did not move. The second one is when I started it in motion and then added another force on the opposite side to balance out. The object was still in motion, however, because the forces were now balanced, the system had a constant velocity. The velocity did not change. Alright, so in this example, we're going to look at a situation where we have wire 1 is affixed to a wall at one end and it's completely horizontal. So let's draw in wire 1. So we have a wall here, and then we're going to have wire 1 come across. One end of wire 2 is attached to the end of wire 1, so we're going to say that there's a junction here. And then the other end of wire 2 is attached to the opposite wall. So we have wire 1 and wire 2. And so the angle between the horizontal and wire 2 is 30 degrees. So there's a 30-degree angle in here. And then here, there is a mass attached. And we want to know what the force of tension in both wires is. Alright, so step 1, we need to identify an object to sum the forces on. Now with equilibrium problems, it's not quite as obvious, but we're going to sum the forces on the junction point where the wires come together. Step 2 is then to identify the forces acting on the object. So on the junction port, we have wire 1, so that's going to exert a force due to tension. And that force due to tension is going to be acting in the negative x direction, because the wire here is going to pull this way towards the wall. If the tension went the other way, this would actually fall down this way. So now we need to look at our next force, so force of tension 2. And force of tension 2 is going to be in the positive x and the positive y, because the wire here is going to pull up like this towards the wall. And then our last force is the force of gravity acting on the mass attached at the junction point. We're assuming the ropes themselves are massless, which we will do for most ropes in this particular course. Alright, we now need to draw our free body diagram. So we have a force of gravity down from the mass. We have a force of tension, 1, that acts in the negative y direction, and then a force of tension 2 that acts in the positive x but negative y. So we can draw in our components. So this would be force of tension 2 in the x, this would be force of tension 2 in the y, and this would be our 30-degree angle in here. Alright, so step 4 is going to be to apply Newton's second law. So we need to identify the forces acting in the x and the forces acting in the y. So when I go look along here, we have force of tension 1, and then the x component of force of tension 2. And then I'm going to leave myself some space to do some math later on, and then I'm going to identify the forces acting in the y direction. So we have force of gravity here, and then we have to remember that we have the force of tension y over here. Alright, so our goal here is to find the force of tension 1 and force of tension 2. So we have force of tension 1 here, but we have only the x component of force of tension 2 here. So we want the force of tension 2 to actually be in this equation. And I can insert this using trig functions. So remember, that we can say that the force of tension 2 in the x is equal to force of tension 2, because the hypotenuse is always the magnitude of the vector, times the cosine of theta, because the x component is adjacent to the angle provided. So we can rewrite this down here as the force of tension 2 times the cosine of theta. So that is now the force of tension 2. It's no longer the x component because we're multiplying the hypotenuse times the cosine of the angle. And I can do something similar down here where I can say the force of tension 2 in the y direction is force of tension 2 times the sine of theta, because the y component is opposite of the angle provided. Now, because the system is at rest, our acceleration in the x direction is 0. So I can say a negative force of tension 1 plus force of tension 2 times the cosine of theta is equal to 0, because 0 times m is still going to be 0. And then I can rearrange to say the force of tension 1 by adding it to the other side is equal to the force of tension 2 times the cosine of theta. So in order to find force of tension 1, I need force of tension 2. So let's try the y direction. The object is not in motion in the y direction either, so this is going to be 0. So we can say that the force of tension times the sine of theta minus, and the force of gravity, remember, equals m times g, is going to equal 0, because 0 times m is still 0. So I can rearrange this to say that the force of tension 2 is equal to m times g divided by the sine of theta. And this information is all provided in the problem. So we can say the force of tension 2 is equal to the 50 kilograms times 9.8. Remember, the minus sign was already taken care of by making the force negative. And then we're going to divide by the sine of 30 degrees. So force of tension 2 is going to equal 980 newtons. I can then plug in up here and say force of tension 1 equals 980 newtons times the cosine of 30 degrees. And that is going to be 849 newtons. So notice when I did my problem solving steps, the unknowns that I was looking for appeared in the Newton's second law equation, so I could plug in my numbers and solve for what I was looking for.